to talk at this meeting. Thanks for organizers to choose this presentation as the oral talk. I'd like to acknowledge the variety of people in this study. That practically was a team effort, put it this way. So most of the people are actually in the audience. So I'll start from Lucia. Lucia is there. And Lucia was a postdoc with us, working on the wave breakup, ice breakup by waves. And she's currently with Daniel Feltham in Reading. So Stephanie is currently postdoc in the National Oceanography Centre as well. Stephanie was working on the rheology. Daniel Feltham was involved quite heavily in that. Tim Williams just presenting, has been just presenting, and we used Tim's expertise on the wave and ice interactions as well. George Nelson, he's mostly mixing guy. He worked on the ocean mixing, open ocean mixing, and CS cloud mixing as well. He helped us. Gurvan Madec, one of the co-authors of the NEMO and OPA ocean model, and probably if you're in this community, you know him very well. Andrew Coward helped us running models at a very high resolution and help with the technical support and basically looking at the parallel programming as well. Many more people actually involved. That was part of the European project called SWARP. So just like to acknowledge the SWARP funding, which ran out as yesterday. We got a confirmation the project has been finally accepted by EU. So we're done basically. So people who were involved in that was Luke Bennett and Laurent Bertino and Vernon. So Daniel Dumont also in the audience. So there's actually a lot of people related to the project. Yeah, I'll try to run it. I'll try to avoid equations. Try to run this animation first. Yeah, that's some kind of picture to show a motivation. So that's a very high resolution coupled modeling exercise. So ocean is roughly 9 kilometer resolution globally and up to 2 kilometers in the Arctic. So what you see the blue stuff, which is ocean currents. Then you see this sort of wiggly stuff coming around, which is atmospheric precipitation. So this is ocean coupled to the atmosphere and sea ice. You also can see sea ice. So several interesting things going on there. First of all, different time scales, you can see that. So time scale in the atmosphere is much shorter as compared to the ocean, but there's a coherence between the atmospheric forcing and the oceanic structure of the currents as well. So, and the reason I showed it is basically the way how the climate models goes at the moment. So the climate models are becoming more and more high resolution, resolving different processes, also resolving different regions at a very high resolution. That's the tendency will probably to continue. And which means we need much more fidelity in the representing the simulations of the ocean circulation, atmospheric circulation, and sea ice. So, yeah, next slide shows the same idea. So if you look from right to left, you can see this classical. This is based on the NEMO model output, but it's true for most of the climate models as well. So the left part is IPCC IR5 assessment report 5. Which has been finished about 2013, and these models usually were at the resolution between 35 kilometers and 100 kilometers. So cross resolution models, they didn't resolve Rossby radius practically everywhere, and you can see the general structure of the oceanic currents, which shows this in color, white high speed, blue low speed, is actually very broad and not localized. And we know this is not right basically from the observations. So if you move to the next panel, this is what next IPCC assessment will be using, and the resolution of these models will be between 10 and 20 kilometers, resolving mostly eddy structures in the lower latitudes, but not resolving eddy structures or boundary currents in the polar areas, specifically Arctic. And that's some kind of future possibility for the next IPCC assessment, which will be using model I just showed you in the previous slide at the resolution about 0 kilometers. These models will marginally resolve the polar areas and Rossby radius in the polar areas, basically simulating to some extent realistically eddy currents, topographic currents and eddies in the ocean basically. So that's some kind of general motivation. So that's where we go, and we practically need a framework to incorporate relevant correct physics, and not only physics but also, for example, biological processes and other things into this type of the models. Okay, so outline. I'll actually dwell a lot on the motivation. That I think is quite important to explain what we're doing and what before we start actually explaining what we do. And I'll talk about the modeling of the marginalized zone, which we implement in the specific model configuration. We're open to the criticism. I know there's several questions which cannot be answered today, even tomorrow and next week, but I think it's a start basically. Then I'll present results of the global model setup and some discussion of the effects of the sea ice fragmentation on the ocean and sea ice. And I'll show the effects of the mixing as well. Again, it's not the perfect scheme we're using, but there's a quite interesting effects there. And I'll show you future projections which don't actually involve waves but have some implication for the wave field as well. And I'll conclude and try to make some kind of question for discussion. Now, the classical motivation, yes, sea ice is retreating, but it's not only that. So left panel, I probably showed it a couple of weeks ago, show two things. First of all, ice is retreating and opening the large areas of the ocean, which are exposed to the wind, and they basically produce the surface wind waves. And also the concentration in ice becoming lower for some period, so which means probably the heat uptake by the ocean is getting higher and ice melts faster. That's some kind of assumption. And if you look at the right panel, it's a general tendency for the last 15 years when the ice actually retreated from the Canadian side, opening large areas of the ocean. So again, probably showed it before, Courtney Strong and Ignatius Riga, and they come up with this assessment from the satellites. So what they did, they pick up the passive microwave satellites from 79, I believe so, until 2012, and we look at the ice concentration areas. For the ice concentration ranges between 15% and 80%, and they call it MIZ, marginal zone, which is arguable or not, but what they come out with, they show that this area is expanding in the Arctic Ocean quite substantially. There's a linear trend over decades, about 30% per 3 decades. And also, if you look at the regional redistribution, this mostly happens from the Canadian side. So East Bering Sea, Chukchi Sea, and also Beaufort Sea. Less from the Atlantic side, which is quite curious. And then the one point which Courtney was here last week, I believe, he pointed out that, yeah, there's a change in the winter. Okay, there's an increase in the summer MIZ, but there's also a decrease in the winter MIZ, and we don't know why. So we sort of try to discuss why it's happening, what we can do to understand that. If you move to the Southern Ocean, the things have become even more complicated because there's a substantial difference between the two algorithms you could use to detect ice concentration from the satellites. So this is so-called NASA team algorithm at the same satellite, and this is the called bootstrap algorithm. And you can see the result is very different. So what it shows the trends in the marginal zone area. Red one shows expansion of the marginal zone. This is also for 3 decades. The blue color shows decrease of the MIZ, basically. So there's a regionality. So like Ross Sea, Lillehammer, Amundsen has expansion. This bit of the Ross Sea shows decrease. This bit shows decrease, and also Weddell Sea mostly shows increase. If you move to different algorithms, you have different situation, basically. So we don't know what's going on there at the bottom line. But it's quite curious because what actually happens, if you look at the publications, for example, by Polo Holland and co-workers, when they look at the changes in the Antarctic ice extent over decades from the satellites, they sort of produce this sort of dipole pattern when they have an increase in the Antarctic ice extent in the Ross Sea, and also that side, and decrease in the Weddell Sea. So some kind of coincidence between the behavior over the MIZ and the changes in the ice extent. That might be quite interesting. Okay, so basically what I think is important to point out again, yes, if we move from the pack ice, when it's ice flows are interlocked most of the time, towards the MIZ we have a dynamical fragmented ice cover. There's several things happen. First of all, the ice became more mobile, that's one thing. There's a higher momentum transfer into the ocean from the atmosphere. Atmospheric boundary layer is also changing. We know this from the measurements from the Ian Flew and Ian Brooks. I think they did measurements of the heat fluxes around Svalbard over MIZ. So the drag coefficient is increasing dramatically, and heat fluxes are changing as well. So there's quite substantial change in the momentum balance transfer between the atmosphere, ice, and ocean. Secondly, if we're exposing large areas of the ocean to the sunlight, we are storing heat in the upper ocean, and we're increasing melt financially. So also ice is thinning at the same time. So there's some kind of mostly positive effects if ice becomes more fragmented. Right, second part, waves. Right, this is the only paper I actually found which actually tried to predict wave heights in the future. It's Horn et al. And they use wave watch 3 model, and I think this was just standalone wave watch 3 they run. what actually happens, yeah, I think it's between 2046, 2065, this decade, and some kind of present climate. They see the increase in the model. This is the increase in the significant heights, and also in the significantly heights above 2 meters as well. There's a substantial increase in the large waves predicted in the Nordic seas and also in the Arctic Ocean. I think it's quite interesting. Right. Another motivation, yes. If you think about the practical application and say, well, why should we care in principle about that at all? Well, if you look at the this plot, which is produced by Canadian service quite a long time ago, Canadian ice services, and what they do usually routine based, and they produce the distribution of the ice parameters in the area where ships go, basically. And if you think about it very carefully, so this is a standard WMO classification called egg code. And this is the total ice concentration. This is partial ice concentration for different ice types and different thicknesses. And this is actually thicknesses according to the gradations of the WMO. And that's fragmentation. This is flow sizes, basically. Right. So this one is okay. This one is okay. This one is not. So no one actually tell you from the model what is going on there in principle. And also, if you look at the satellite in the real time, they can't produce this parameter at all. So some of the models try to sort of to do it. And I'm not claiming that none of the models can do it. There are some pilot forecast, for example, in NERSC, which tries to do this assessment. But as a rule, none of the ice services actually can do the fragmentation right now. Another motive, I had that basic continuation, and that's why the project SWARP was sort of focused on the MRZ. So we tried to produce a basically pilot scheme to calculate flow size distribution for the forecast, and team was involved, and NERSC is running the pilot forecast right now. And it was part of the GMS services for Copernicus. And another motivation, it's the fact that it's not only resolution which is important for the future climate simulation. There's also the fact that we're moving towards the Earth system modeling as a community. So more and more we are involved in the coupled modeling between the ocean, sea ice, glacial ice, atmosphere, land surfaces as well, and biology, basically. So currently the main direction of the trend is to use the Earth system models for the climate assessments. And again, there are two things here. First of all, some of the organizations like NetOffice try to produce the seamless forecast, so they try to use the same modeling technology for the range of the resolutions and temporal resolutions as well. And generally, it means that the simulations are becoming become a much higher resolution, basically. So we're talking about the tens of kilometers of resolution. And they're also quite detailed in terms of the frequency of the output. So that's quite important. And just an example, this one of the runs we produced the NERSC, and we looked at the primary production of the biology, which means chlorophyll and phytoplankton, zooplankton. What actually this plot shows, and that's some kind of current state from the model. It shows, for example, Arctic is not producing anything much. And then if you move to the future towards the end of the century, there's quite a substantial shift in the productivity in the Arctic and North Atlantic. So Arctic becomes slightly more productive, but Atlantic becomes practically bare, basically. And that has a quite substantial implication for the planning of the fisheries and quotas and stuff like this, basically. So it's quite important for the climate assessment and the impacts on the society. Right, okay, so that was motivation. So there's several motivations why we actually bother to look at the improved physics of the sea ice and ocean interaction. So the idea we tried at this specific project, we tried to basically combine the information of the waves and see how it affects the sea ice dynamics. Specifically look at the fragmentation of the sea ice by the waves, and the sort of three parameters involved in that. We have on the sea ice side, we have ice thicknesses, concentrations, and flow sizes. And then, because of the fragmentation, there are changes, potential changes in the rheology and the dynamical response of the sea ice, which also feedbacks into thermodynamics. So if you have a dynamics which makes ice divergent, you change the heat contents of the upper layer, you also change thermodynamics. And then some kind of loop basically feedbacks into the flow size evolution, and then it could feedback into the fragmentation and wave attenuation in the ocean. So that's some kind of framework we work with, basically. Right, it's just picture show what we try to implement. So we look at the fragmentation of the sea ice due to waves, and we have the advection of the surface waves into the sea ice, and also attenuation of the ice covers. Again, there's a discussion whether it is done in a completely correct manner or not. Well, that's a discussion. We use the lateral melting schemes when we use the mean flow caliper to melt ice, and we also use the some schematics to allow for the, for example, the initialized phases, and then we look at the how the collisions affect the rheology, and specifically how it affects the rheology and flow size distribution. So this sort of two slides show what actually we did in terms of the wave attenuation, and also in terms of the flow size distribution of the wave attenuation. So terms in the flow size distribution includes wave breakup, thermodynamics, growth and melt, also the potential contribution from the collisions, which we actually don't explore much, and also the advective component of the flow size, which we implemented in the model. And then the change in the waves includes the change in the wave spectrum due to the attenuation of the ice, plus non-viscous losses and nonlinear interactions, basically. Okay, and that's came from one of the papers. I think it's a Danidi one paper probably, and it just explains general mechanics of the breakup which we used. So bending of the ice plate, and two criteria is used. We actually use the strain criteria and the stress criteria. So if the flexural stress increases the threshold, the flow breaks, and if the strain reaches the critical value, it also breaks, basically. So, and ultimately we will break an ice in two according to the half of the lane legs, and there was some kind of procedure to produce the mean flow size from the maximum flow size, which is produced from the waves, basically. And, right, and we used attenuation of the waves using the basically tabulated coefficients for the wave attenuation according to the periods, ice thicknesses, and I think the flow sizes are involved as well with this one. I'm going to show here. Right, so that was a breakup. So the rheology, so Stephanie covered this on Monday, but just have to show this couple of things again. Yeah, so this is basically the formulas which allow the smooth transition between the classical pack ice rheology, for example, EVP, or actually any other rheology in principle, to the collisional behavior, and we still operate within continuum limits, so it's not discrete element model and something like this, but it's a smooth transition. So we do not prescribe MZ. So people ask, how do you prescribe MZ? We don't. We just calculate it, basically. And then, depending on your diagnostic criteria, you could produce a diagnostic MZ area, visa, and so on, basically. So, and we are using this notion of the turbulent pulsation of the ice drift to create the basically a measure of the turbulent pulsation and embedded in the rheology, which is we use as a switch, or some kind of, not switch, but smooth transition between two rheologies. And they, well, that's just on a momentum balance, and we just look at the tensor, internal stress tensor, and it's just a linear combination of the frictional, so-called frictional or pack ice rheology and collisional rheology. And the formalism is such that it's practically this has the same form, which is very useful when you do numerics with this. Okay, right. And then just switching to the actual model setup we used. So I'm not going to talk about this in very much detail. So if you're interested, there's a website over here, and this is the European modeling framework called NEMO, and that's basically the plot from the website. So there's the whole variety of information there. You could get the code from there, basically. You could get manuals and publications. You could see what it's all about. Now, what I'm going to just go very briefly. So that's model configuration we use for the study. So NEMO is a oceanic part, which consisted of OPA model. This is French one, and we run actually run at two resolutions. We run mostly at the 1 degree resolution, but also quarter degree resolution, which means I'll show the NEMO grid, which means that in the Arctic Ocean we are around 35 kilometers for the 1 degree and 14 kilometers for the quarter degree. And then this model is coupled to the Los Alamos size model, and we typically run multi-decadal runs, and we force the model with the atmospheric analysis. Usually we're using the ECMWF forcing field. Sometimes we use NSEP as well, but that's some kind of choice. And we also had this information on the waves constituting the significant wave heights, peak periods, and also the growth velocities from the same forcing field base. So we have a consistent forcing of the waves and atmosphere. There's a masking procedure involved because the CIS mask in the forcing field and in the model do not correspond to each other, so we have to remask the fields in a special way, and also advect the wave information where there's no information in the forcing fields. And then we use the flow size breakup by waves, and also advection of the flow sizes and thermodynamics, which I described earlier. And we also use reconstruction of the flow size distribution from the maximum and mean flow size from the average flow size according to the power law, which is a bit of weakness because we know it's a question of whether the flow size distribution follows the power law or not. But we use some kind of approximation published by several people who try to fit different coefficients into the power law and experiment with that. And finally, we use this combined elastic viscoplastic collision rheology I described before. Okay, right, OPA model. So main thing I mean, if you know about ocean modeling, don't pay attention. So if you don't, a couple of things which are important. So this is the spherical X approximation. So basically the gravity is vertical parallel to the Earth radius. Thin shell approximation, so ocean depth is quite small as compared to the Earth radius as well. We use turbulent closures to look at the turbulence in the vertical, and some parameterizations sometimes to look at the horizontal turbulence as well. It's Business approximation, so density variations are negligible in the buoyancy force. We use hydrostatic option, so practically we separate convection and the sort of geostrophic behavior of the ocean. So convection is parameterized, and we use incompressible liquid as well. Right, as everything is just discretized on the grid, so left it's a NEMO grid, and the reason I should show this because size and NEMO grids are slightly different. So NEMO grid has the so-called tracer where tracer points, a tracer node, which we use to calculate salinity, temperature, and other parameters in the middle of the grid cell. So this is finite difference grid basically, and the velocities were actually on one face of the cell, another one. So this is U velocity, and this is V velocity. If you go to size configuration, you have tracer field in the middle of the cell, but you have velocities in the corners. So some regridding procedures are involved when you try to couple size model and NEMO. And that's a grid. So NEMO grid, that shows, this is 1 degree, but I think it shows every fourth grid line basically. So it looks quite coarse, in reality it's very fine basically. So NEMO grid has 3 poles. It's called so-called tripolar grid, but people argue it's actually bipolar grid. It's rather than tripolar. So one pole is in Canada, another one in Siberia, and there's a geographical south pole. And there's some kind of features called North Pole, just goes across some kind of singularity, and you need boundary condition there as well. So if you look at the Arctic Ocean, that's what you see, and yeah, that's 2 poles, and that's a singularity line basically. So you need really not only cyclic boundary condition on the east-west, but also boundary condition along this line. Okay, and this is run on the big machine, and this actually pictures the previous machine factor, but we are running on the machine called Archer at the moment. This is national high-performance computing resource, and we are moving to the new machine probably next year or 2. And the thing is, everything is parallel, so we practically use a very large number of processes, about 10,000 processes to run the model. And the whole domain is split, so each information goes on a single process, and then processes talk to each other, basically. Right. Just some examples what happens if you run the model with ice fragmentation. So that's wave heights we're using, and this I'm sure which period. I think it's probably winter looks like maybe. Yeah. So one point here is yes, if you sort of look at the gradients of the wave heights in the open ocean sea ice, you have a quite strong gradient, so they attenuate quite quickly. And according to that, yeah, that's summer, this winter, that's summer basically. So according to that, the flow size is also has a very strong gradient. So you have small flow sizes at the outer edge next to the ocean, and then they grow. The flow size increase, very increase dramatically towards the ice pack. The same for the Southern Ocean, and it's quite a striking picture as well. So you can see very strong gradients in the flow sizes, which corresponds to the breakup. So basically, yes, the model shows yes, wave do attenuate quite fast, and there's no breakup in the inner ice part of the ice. This picture, I'm sure I showed this before, but it's basically to show the fine structure. This is quarter-degree resolution model, and resolution in Nordic seas is about 15 kilometers. So you can actually resolve features like Odin. I mean, I'm not sure whether this specific year did have Odin or not, but there's features which could be associated with the realistic behavior of the ice in this area. And in this case, there's attenuation of the waves, and there's a change in the flow sizes. There is sort of quite small flow sizes procured by waves, but there's associated attenuation of the waves. What effects it has? Well, there's some effect regarding the thickness and the concentration changes, mostly related to the lateral smell. So I'll show this summer averages, and I think it's a long-term average, about 10 years. So to the left is some kind of control ice thickness, to the right the sensitivity between the run with the fragmentation and the control run. So you can see a reduction of the ice thicknesses around the ice edges, but there are also changes in the Canada part, which is related to the fact that the flow sizes which this round is usually is not equal to the standard one used by the size model. And if you do try to separate the things, for example, if you look at the tendency in the ice volume due to dynamics, again, there's a quite strong signal in the outer ice edge and marginal zone, but there's some signal in the middle of the Arctic Ocean due to the fact the flow sizes are different. And then it's evidence that larger melt has quite substantial impact on the change. Because larger melt is larger, so basically the heat which is stored in the upper ocean mostly goes to the larger melt. So the residual part it's a basal melt. So actually basal melt it's smaller basically. So so next part is it's about the mixing. So Stephanie presented this in the meeting in Bangor in July, I believe. So the idea is to try to experiment with the different mixing schemes which account for the wave mixing. So currently NEMO has some kind of two options. None of them is realistic. So one of the options is just switches off completely the mixing due to the waves where there's ice cover. Even ice cover is very the fraction of ice cover is very small. Other option is it doesn't account for ice at all. It just mixes ocean in the same way as if it is the open ocean. So Stephanie tried to sort of look at that and implemented this scheme which accounts for the actual wave heights, including attenuation in the size. And then for calculating the roughness parameter, the thermokinetic energy flux into the ocean could be calculated, and this has effect on the ocean vertical mixing of the ocean. And that's been done for the so-called generic length scale mixing scale, which is one of the standard options in NEMO. And that's some kind of curious effect, because there's two things. First of all, the mixed layer in the Arctic became shallow. This is the winter one. And there's also response. Actually, they have differences, but there's also response in the thicknesses in the Arctic Ocean due to the fact that there's a difference in the heat flux through the mixed layer in different areas. So some of the areas has more heat flux, some of the areas has less heat flux, basically. And there's a corresponding change in the concentration as well. So there's quite substantial sensitivity to that. We're not saying this is right. It's some kind of sensitivity study which tells you, okay, there's a sensitivity to the mechanism which might be accounted for. The last part of the talk is about the projection. So the way how we did it, we just decided to cheat a little bit, because currently we can't run the high resolution projection including waves. So it's very expensive, we can't do that. So what we did, we ran this high resolution projection for the ocean and sea ice using the Hadley Center atmospheric forcing field. So we sort of switched off the feedbacks between the atmosphere and the ocean and the rest, basically. And we ran it for 100, actually ran it for more than 100 years. You can see that from 1870 to 2099. And the reason was to look at the general behavior of the sea ice and changes in the ocean, and potentially get some kind of conclusions what wind is doing, basically. And so this specific plot shows the sort of current climate state for the summer 79 to 2005 average. And it's just ice extent, which is shown this in color, but there's also these numbers which I'm sure you could see or not, the pink one. And they show the mean flow sizes calculated from the ice concentration, not from the fragmentation model, but just using the parameterization developed by Christoph to relate the ice concentration to the with the mean flow sizes. And what it actually shows that generally, there's a quite small flow sizes around ice station, the Barents Sea and also Kara Sea in summer, but generally ice flow sizes increase towards the Central Arctic quite substantially. So if you go into the future, and first of all you can see the ice retreating. Whether it's retreating in a realistic manner or not, that's another issue, because maybe it's not completely realistic, but you can see that there's quite substantial reduction of the ice concentration in this area, which creates, according to Lucas representation, leads to this wall of flow sizes basically. And the assertion is, yes, if the ice retreats, it became less compact, so potentially your flow sizes will decline basically. That's what it shows. Right, so this just plot to show where this run actually stands in terms of the CME5 simulations. So this is the standard CME5 ensemble run for the several concentration scenarios here, and 2.6, 4.5, 4.5, 5, and 8.5. And the run we use dash all this sort of magenta line, yellow line here, and the light blue line over there. So just they show that actually within the ensemble, they're not outstanding around. They're some kind of reasonably all right. And this is the which one is which? Yeah, I think this one is summer's winter. I can't remember which one. Yeah, that's probably some on the left. So they're practically within the ensemble of the CME5 simulation. So not outstanding. Right. This plot probably we showed before. Just explained that yes, okay. According to the simulations, the marginal zone on close ice area should be increasing dramatically around mid-century basically. So that's the idea. And if you look at the observational data from Rigg and Strong, which is shown here, they have some correspondence. So they show slightly different parameters. But this is just effective width of the MIZ in the Arctic Ocean, and this is the relative area of the MIZ as compared to the total ice area. But they show the same tendency basically, and curiously enough. So they have this increase in the summer MIZ area and decrease in the winter MIZ area. Okay, right. Other thing which what we found with this run, it's on the right. It's the fact that ice becomes quite thin. So the large flow shows ice volume, and the insert shows ice thicknesses. So and the color they represent different decades. So which one is which? So the current state is red, basically, and then the decade 2059 2059 is in green, and the next decade 60 to 99, actually several decades, they are in yellow. So by end of the century, the ice is quite thin. This is the mean ice thickness for the Arctic area. So we will face potentially very thin ice. That's and also the seasonal cycle, which I think starts shifting a little bit towards the maximum early on as compared to the current climate. So the left plot just shows the comparison to the time ice, just to see how far model deviates from the current ice thickness or ice volume analysis. So it's practically slightly on the high side, but it's not dramatically bad. Okay, so this bit shows some kind of assessment what may be happening with the wind. Because we don't have waves there, we can't do that, but what we can do, we can look at the wind field in the frozen field and just have some assessment what happens with the wind in terms of the change. So that's wind speed at the 10 meters height, average for the present climate 2000-2009 in winter. So, well, Arctic is actually does have very large values, it's about 5 to 6 centimeters per second in Central Arctic, and also high wind about 7 meters per second in the Barents and Kara Seas. There's an increase in wind, and generally in the Central Arctic area that we expect. So, looks like the actual wind increased probably by 30% roughly, maybe 40 as compared to the current climate. And corresponding wave change is roughly that. So we expect the wave to increase potentially by roughly 50 to 30%. That's some kind of assessment. If you go to the Southern Ocean, it's probably less dramatic. So in a way, again, this is the sort of current climate picture. It shows the strong winds around ACC, but then they decline towards the continent. There's an increase in the ACC area. It doesn't seem to be much of the increase in the area covered by sea ice, but there's quite some increase in the ACC area. So potentially, we look at the wind heights increasing by maybe 20% plus, basically. That's some kind of assessment. Right. I sort of try to cover a lot of subjects. I talk about the general ice modeling for the MZ in the OGCMs and the motivation to do that. And I talk about some processes which we implemented in the OGCM configurations, including breakup, flow sizes, and origin. And I talk also about the effects of the flow sizes on the ice in ocean. So Stephanie in her talk on Monday talked about the impacts of rheology on the ocean sea ice as well. I presented some ideas for the future projections in the high resolution models, and this is interesting bit. So what next? Well, one thing we keep discussing in the community, specifically NEMO community, sometimes actually beyond that, because GFDL was also involved in this. We're talking about the coupling between the atmosphere, sea ice, ocean, and waves. So it's a very large exercise, and it's quite complex. And there are several issues there. It's not that simple, unfortunately. Specifically, there's a activity within the NEMO wave working group which deals with that. It looks at the ocean waves interaction without sea ice. So they look at the global models, but they don't take into account the wave attenuation, just basically have a cutoff where sea ice is 30% of concentration, all of this. And one of the things I'll show with the next slide, it's important because it actually was substantial change in the coupling mechanism between the atmosphere and the ocean, because there's a Stokes correlative effect, that's one thing. There's also change in atmospheric and oceanic stresses because of the waves. So part of the energy goes on the waves, the drag is reduced basically. And it's completely unclear to me how this could be played when we have a sea ice basically, because I think at the moment there's some kind of semi-consensus how to do it for the open ocean. I don't think there's a consensus how to do it for the sea ice for the global models. And this slide came courtesy of Ovin Breivik, and which is a bit fuzzy, but basically what there's several points here. So this cartoon shows what happens here. We've got a wave, you've got this at orbital velocities, and there's atmospheric drag, oceanic drag, and they have a breaking wave. So that's what happens in the open ocean. That's part of the significant input into of the energy into the mixed layer and actually increasing the ocean mixing. This doesn't happen on the sea ice. That's one thing. Then there's also a reduction of the or change in the mixed layer, and also changes in the sizes as well. That's this point here. Again, if you do the ice, if you do the wave attenuation by sea ice, and if the fragmentation of the sea ice is very important for the drag coefficients, that needs to be considered how these things add up together. And one thing is quite curious. So there's quite substantial work on the Lagrange circulation in the open ocean. It's clearly, well, it's not relevant for the sea ice characteristics per se, but if you look at the aerial photography around ice age in the Southern Ocean specifically, you can see these bands, and you can see there's actually Lagrange circulation is there. So if your ice concentration go down substantially just outside the ice age or just inside the diffuse ice age, there's a potential effects of the Lagrange circulation. Again, I'm not sure it's important or about that. There's a sub-physical mechanism which maybe we could consider. And thank you, and questions.
Questions?
Thank you. I could ask how far away is the contribution from the Stokes drift? Is it orders of tens of magnitude smaller than the other effects, or is it like a factor of 2 or 3?
I think it's. You mean on the current on the ocean circulation as a contribution? I think it's about 10%. 10-15%. So it's not negligible. It's not very large. It depends on the wind condition. Clearly, it depends on the waves, but it's yeah.
Okay, so then I can follow up, because I did some experiments recently with one of my colleagues, and it turns out that the vertical shear of the Stokes drift is much enhanced because of the streaming.
You mean the Coriolis effect?
No, because of the boundary layer streaming below the waves or below the ice or whatever.
Okay.
So maybe if you double it, maybe it becomes more interesting.
Yeah, it could be.
The effect is actually very, very strong.
Yeah.
It's a JFL publication.
I don't think we know the answer. That's the point, because most of the analysis comes from the open ocean.
Yep.
So there's no much analysis yet on the either diffuse sea ice areas or well, compact ice area. Clearly, we don't have this effect. But yeah, it could be probably estimated, but I don't think there's I don't know whether any measurements addressing that first. And secondly, in terms of the modeling framework, it's not there yet. That's one thing which probably needs to be discussed.
Yeah. How confident are you that the increase in the marginal ice zone area is real? I mean, this question for both, for the past 40 years from the satellite data, can we believe them in this respect, and also for the model for the projections you showed for 50, 60 years?
You mean for the Arctic? Or for Antarctic? For the Arctic?
The Arctic, yes.
I had a chat with Courtney Stone last week, and basically said they use different methods because they are aware about this not biases, variation in the assessment from different satellite technologies. So they use different algorithms. You arrive to different answers. For example, for Antarctica, I think his statement was basically yes, the result is quite robust. I'm not a satellite person. I just take what they tell me basically, and say the result is quite robust in the Arctic. In Antarctic, it's a different issue. It's a bit unclear at the moment, but for the Arctic, they're pretty confident. They published a paper this year, I think. They tried different methods to estimate this. Yeah. So that's probably a reasonably supported trend, I suspect.
The Office of Naval Research has recently completed a study of the marginal ice zone in the Western Arctic, MIC program, and I think it's interesting that they found they had many arrays of wave buoys that were placed out in the spring and then lasted through the summer period. And what they found is that the wave activity is not very strong during the summer period when the marginal ice zone is really happening. And I think what's happening, at least in the Western Arctic, is that there's more of a sense that a process called flow fragmentation due to thermal effects might be a bigger factor in producing the smaller flow sizes that are characteristic of the marginal ice zone. There's a paper by Stephanie Arndt and Don Perovich and Arnold Song and I think Chris Poloshansky in the GRL that discusses this in some detail, and it fits in with the idea that the marginal ice zone may be increasing over time because the mechanism that they're talking about is actually based on the thermal fragmentation that's due to the melt ponds, and there's been a big increase in melt pond activity in there. But I think it's pretty significant that the wave action in the summer period is very weak in the Western Arctic, and may not be a cause of the marginal ice zone.
Yeah, I agree with this. I mean, sort of, Danny sitting next to you, you probably could support this view as well. So yeah, it's a combination of the factors. That's what this sort of simplified line of equation we put in. So different sources for the fragmentation, basically, it's either waves or thermal one, just like melt ponds, for example. Yes, we haven't got to that stage, at least for these simulations, when we actually tried it. But there's a sort of ongoing project within Region, for example, look at the melt ponds and the effects of the ice fragmentation of that. So there's an effort towards it. We did have a meeting 2 years ago in Auburn on the flow size distribution and organized by NAR, basically. So we did discuss part of this. And there was the same question raised that yes, in some cases, waves are not the cause, basically. It's a thermal effects could be, yes. Sometimes, yeah, but I mean, my take on this, I think it's important if the physics and some aspects of the physics were presented in details. I'm pretty sure they're wrong, put it this way, right? So maybe imperfect, but I think it's a framework because what we need from the climate modeling perspective or general large-scale ocean modeling perspective, we need a framework where we can put the physics we trust into the model. So that produces a framework. At least we know roughly what we need. And then we could iterate with the ice physicists or people look at the mixed layer or waves, how we can improve this. But at least from our perspective, there is a framework which potentially can be used at least at this stage, because I know there are the parallel efforts going on in different places. NCAR, IPSL in Norway, in New Zealand, in Australia, so people actually doing very similar things basically. And it seems to be the framework very similar to what I have presented, not exactly the same, it's actually emergent. I think it's one of the important points, because frankly speaking, we had a very long period of stagnation in the subject, which lasted for 20 years. Not stagnation per se, but the results from the physical processes studies and small-scale modeling was completely disjointed between these results and approach and the climate modeling. I think we are coming together now. Let's say I think it's a great thing basically. So if we can formulate a framework where we could work together towards a common goal, I think it will be quite important.
Before we finish, I'd just like to remind you there's a seminar this afternoon. It's at 1:30 by Gerard Ayus. I guess it's here, is it, Emile? Yeah, Gerard. Yeah. I guess
It's not so important.
any more questions? Yevgeny?
Treating it as a different.
I'm interested in your last comment. You said last 20 years there's a disjoint between the physical process people and climate modelers. Do you know why?
Okay, right. So wave modeling, especially modeling ocean waves, NCS, it's extremely hard. We know this. We saw it basically. It's very hard to put the correct framework for that particular work, and it's very hard to solve it. And that's one of the reasons I think. Observations to verify the results from the process modeling, it's very difficult to get. So to put a buoy in the MRZ takes a lot of money and effort, basically. We know this again. And it's several projects which are facing. So this sort of a reason from the process modeling part. And then the climate models. Maybe we didn't have enough influence to explain. So this mechanism or process actually might be quite important. That's one reason. Maybe climate models were not ready for that because they were cross-resolution, very crudely parameterizing. Just general oceanographic process like mixing was very crudely parameterized. So I think there's a general separate development of these two things. I think that the fact that the climate models are becoming at the more and more high resolution actually helps to join these things together, because if you're at the high resolution, you need to consider edges, you need to consider sea ice concentration gradients or density gradients due to ice melt, for example. You need to consider these things basically. And these processes may not necessarily be of the first order, but at least they might be of the second order, and maybe first order for the regional purposes. I think anyway, that's my view. I mean, I'm not saying I'm right about it. But.
Okay, well, thank you again, Yevgeny.